The first crew to Mars won't just be exploring, they'll be finding out in real time whether humans can actually live off Earth at all. In this video, you'll follow their full journey. The long radiation-filled trip through deep space, the one-shot landing in Mars's thin atmosphere, and the constant fight to keep air, water, power, bodies, and minds stable on a planet where a single failure can end the mission in minutes. You launch, you reach orbit, and then the key maneuver happens, trans-Mars injection. The engines fire for several minutes and push your spacecraft onto a new path around the Sun. You are now on an elongated orbit, an ellipse, that starts near Earth's orbit at about 150 million kilometers from the Sun and stretches outward toward Mars's orbit at about 228 million kilometers. You're not heading straight to Mars. You're falling around the Sun on a carefully chosen curve, and Mars is moving on its own curve. The whole mission depends on those two paths crossing at the same time. Even at the best launch window, Earth and Mars are still tens of millions of kilometers apart. Closest approach can be around 55 million kilometers, about 34 million miles. That is more than 140 times the distance from Earth to the Moon. Out there, your entire world is a pressurized cylinder or cluster of modules, maybe the size of a small apartment or bus, moving at tens of kilometers per second. The outside environment is hard vacuum, extreme cold and heat, and constant radiation. There is nowhere else to go. So you might ask, if things start to go wrong in that long fall, can you just turn around and come home? The answer is basically no. Very soon after leaving Earth, within days, you pass a point where a powered return using current chemical rockets is not realistic. Early on, you still have some flexibility. You can adjust the path, tweak the timing, correct small mistakes. But to actually stop, reverse direction, and fall back to Earth would take far more propellant than your spacecraft can carry. The energy cost explodes as the distance grows. That means this mission is not like the ISS, which orbits only about 400 kilometers above Earth. If something breaks on the station, you can send a cargo ship in weeks or a crew in hours. On the way to Mars, once you are on that interplanetary trajectory, there is no rescue ship. There is no abort to Earth mode. If you suffer a major failure 30 million kilometers from home, you and your crew are the only ones who can fix it. Radio messages already take minutes to go one way. By the time Mission Control on Earth understands your problem, you have already lived with it for several minutes and maybe made the key decisions. So you are locked into this long, one-way fall. While that is happening, what is this environment doing to your body? From the first day you're in microgravity, your body is tuned for 1G. Remove that pull, and everything reorganizes. Fluids that normally collect in your lower body move upward. Your face looks puffy, your legs look thinner, your sinuses feel blocked, your eyes experience different pressure. Some astronauts on long missions report changes in vision that can last after they come home. Your bones and muscles are another big problem. On Earth, just standing and walking loads your skeleton. In microgravity, that load is gone. Without heavy exercise, you can lose around 1 to 2% of bone mineral density per month. That is like fast-forwarding aging in your skeleton. Muscles in your legs, back, and core shrink because they are not needed to hold you up. Even your heart weakens a bit because it no longer has to pump blood against gravity from your feet to your head. So exercise becomes non-negotiable. Astronauts on the ISS already work out more than 2 hours per day using treadmills with harnesses, cycle machines, and resistive equipment that simulates lifting weights. A Mars transit will demand at least that level of training, inside cramped modules with limited power. Skip too many sessions and you may arrive at Mars too weak to safely work in a spacesuit, climb ladders, or deal with emergencies. While your body is adapting, your spacecraft is doing something just as complex. It is acting as a tiny closed ecosystem. You carry a limited mass of water, oxygen, food, and spare parts. You cannot just vent air and refill it. You have to recycle almost everything. On the ISS, roughly 90% of water is recovered. A Mars ship has to push that number even higher because resupply is not an option. Water from sweat, breath, and urine is collected, filtered, distilled and turned back into drinking water. The air system constantly scrubs carbon dioxide using chemical cartridges or regenerative systems so you do not slowly suffocate on your own exhaled gas. Condensed water on walls and equipment is captured. Some concepts add small biological units, algae tanks or microbial bioreactors that help recycle waste and stabilize the air chemistry. In this environment, a leak is not just annoying, it is a serious threat. A small crack in a pipe can slowly drain a water tank. A failure in the CO2 removal system can let levels creep up and cause headaches, confusion, and eventually loss of consciousness. Filters can clog. Valves can stick. Every component is part of a chain, and the chain has to work for months without outside help. You're not just passengers, you're technicians living inside your own life support hardware, running checks, swapping filters, and restarting systems as if your life depends on it, because it does. All of this is happening on a path that we did not design from scratch for humans. We borrowed it from robots. For decades, robotic spacecraft have gone before you. Orbiters and landers like Viking, Pathfinder, Spirit, Opportunity, Curiosity, Perseverance, and Insight have already flown interplanetary trajectories to Mars. Their navigation data, fuel margins, and failure modes define the safe zone for your mission. When your crew makes a mid-course correction burn, the timing and size of that burn are based on models that have been tested by these earlier flights. If a probe used too much fuel correcting a certain kind of error, planners know to avoid that profile. If another mission came in on too steep an angle and nearly burned up in the Martian atmosphere, that becomes a limit in the design tools. You're operating inside an envelope that robots proved is just barely workable. The first crew is not guessing. You're using decades of hard-won statistics from machines that either made it or died trying. So you get this picture. Months in microgravity that slowly change your body. Inside a ship that must behave like a closed world. On a flight path that cannot be aborted. Built on the edge of what our robots have survived. That is the baseline cost just across the space between the planets. But there is a layer on top of all of this that you cannot see or feel directly. The constant radiation that hits you the moment you leave Earth's magnetic shield. So the question is, if surviving the fall through space is already this hard, what happens when you add a radiation environment that slowly eats away at your DNA from the inside out? How dangerous is space when you feel perfectly fine and nothing hurts, yet it's still slowly damaging you? Once you leave Earth's magnetic field, you're exposed to a kind of radiation that you never experience on the ground. Not sunlight, not X-rays from a hospital, but galactic cosmic rays. These are atomic nuclei, protons and heavier elements like iron thrown out by supernovas and other violent events in the galaxy, moving at close to the speed of light. You don't see them. But they are hitting your body, your ship and your electronics all the time. Detectors on Mars-bound spacecraft have already measured what that means in numbers. On the way to Mars, you can expect something like 0.6 to 0.7 millisieverts of radiation per day. Over a 200-day cruise, that's about 120 to 140 millisieverts just for the trip out. That is roughly the dose from a few dozen CT scans of your chest. And remember, that's only one way. You still have to live on Mars, then come back. A millisievert is a unit that wraps up how much energy the radiation dumps into your tissue and how biologically harmful it is. At these levels, you're not going to drop dead on the ship. The problem is long-term damage, higher lifetime cancer risk, damage to blood-forming cells in bone marrow, and subtle hits to your brain and nervous system. The cruel part is that galactic cosmic rays are very hard to block. Many of them are so energetic that even thick shielding only slows them down a bit. Some go straight through meters of material. So the background radiation dose in deep space is something you have to accept and manage, not something you can fully remove. But cosmic rays are only one side of the radiation threat. There is a second, more volatile one that can jump out at you with very little warning. What happens when the sun suddenly decides to throw a tantrum straight at your ship? That's when you get solar energetic particle events, bursts of high-energy protons and other particles linked to solar flares and coronal mass ejections. Most of the time, the sun is relatively quiet, but a single big event can boost the radiation around your spacecraft by a huge factor in just hours. We have a scary example from history. In 1972, between the Apollo 16 and Apollo 17 missions, the sun produced a very strong flare. If astronauts had been in deep space at that moment without proper shielding, the dose could have been high enough to cause serious radiation sickness or worse. The only reason we didn't lose a crew is timing and luck. No one was out there during that event. A Mars ship cannot rely on luck. That is why future designs include a storm shelter, a small area in the spacecraft with extra shielding wrapped around it. You pack the walls of that space with water tanks, food supplies, and other hydrogen-rich materials that are good at stopping solar protons. When solar monitors and satellites warn of a big flare, the crew moves into that shelter and waits it out, maybe for several hours, maybe for a day or more. It is cramped and uncomfortable, but it could be the difference between a survivable dose and a mission-ending medical disaster. This sounds simple. Add more shielding. But the physics of shielding deep space radiation has a nasty twist. Why not just cover the whole ship in thick metal and be done with it? Because with the most dangerous part of the cosmic radiation, those very high-energy galactic cosmic rays, heavy shielding can backfire. When a cosmic ray made of a heavy nucleus slams into a thick layer of metal like lead, it can break apart and produce a shower of secondary particles. Instead of one heavy particle, you now have many lighter particles spreading out. Some of these secondaries can actually increase the total dose inside certain parts of the ship. That is why mission planners are more interested in materials rich in hydrogen, like water, certain plastics, and, once you're on Mars, regolith piled over habitats. Hydrogen does a better job of slowing and stopping incoming particles without producing as much harmful secondary radiation. So the inside of a Mars ship will likely be arranged not just for comfort or convenience, but for radiation protection. You might place water tanks, food stores, and even waste containers in specific locations to create a protective cocoon around crew sleeping areas and workstations. Your storage plan doubles as armor. You are literally using your own supplies as a shield. Even with these tricks, you are still taking a serious dose. And that brings up a tough question. How much radiation can one astronaut safely take over a career? Space agencies already set career limits on radiation exposure. They know that above certain levels, the added risk of cancer later in life becomes unacceptable. On the International Space Station, astronauts get a higher dose than people on Earth, but missions are usually about 6 months and still within those limits. A full Mars mission, travel out, time on the surface, travel back, can easily run 2 to 3 years. When you add up radiation from the trip, plus the time on the Martian surface where you still have more radiation than on Earth, many mission profiles end up at or beyond current career limits. That means a single Mars mission could easily use up most or all of an astronaut's allowed lifetime exposure, and the cancer risk is only part of the story. Research with animals, especially rodents, exposed to space-like radiation in particle accelerators suggests there may be direct effects on the brain and nervous system. Some studies show changes in memory, learning, and anxiety levels at doses similar to what a Mars crew might receive. Translating that to humans is not exact, but it raises real concerns. Will long-duration deep space radiation subtly change how crew members think and behave over time? Will it affect mood, decision-making, or reaction time in ways that are hard to notice until it's critical? Because of this, radiation turns into something more than a medical statistic. It becomes a core piece of mission design. How much time can you afford to spend in deep space before the risk becomes too high? That question drives almost everything. If you can build faster propulsion that cuts the trip from, say, 8 months to 4 months, you nearly halve the transit dose. That's a massive win. But faster propulsion usually means harder engineering, more mass, and higher cost. Mission planners have to trade money and complexity against radiation risk. The same logic applies to how long you stay on Mars. The surface dose on Mars is lower than in deep space because the thin atmosphere and the planet itself block some radiation. but it's still several times higher than the average on Earth. So your total mission time, transit plus stay plus return, is a radiation budget you cannot exceed. Even astronaut careers will be shaped by this. You might have people who can fly several missions to low Earth orbit, but only one to Mars. For them, stepping onto that Mars-bound ship is like cashing in decades of safe exposure in one intense trip. After that, they could be grounded not because of poor performance, but because their body has simply taken too many millisieverts. So now you have this picture. You are locked in a vehicle with no quick escape, in an invisible storm of high-energy particles that never really stops, facing both known and unknown biological effects, and your entire mission timeline is designed around not crossing a line your body can't tolerate. If that is the cost of just reaching Mars and surviving the crossing, what happens when you finally arrive and have to rebuild your body under a gravity that nobody has ever lived in long-term before? By the time you reach Mars orbit, your body is not the one you left Earth with. You've been in microgravity for 6 to 9 months. Even with heavy exercise, crews on the ISS can lose up to 20% of their muscle strength over 6 months, plus a clear drop in bone density. That is with more than 2 hours of training every single day in a place where they are not also preparing to land on another planet. So when you finally get to Mars and it's time to go down to the surface, you're not arriving fresh. You are already deconditioned. Your legs are weaker. Your back muscles are weaker. Your bones in your hips and spine are thinner than they were at launch. Then you ask that weakened body to deal with gravity again. Not full Earth gravity, but about 0.38 g. On the surface of Mars, you weigh a bit more than 1/3 of what you weigh on Earth. In metric, if you are 80 kilograms on Earth, your weight on Mars is equivalent to about 30 kilograms of force. In pounds, someone who is 180 pounds on Earth would feel like around 68 pounds on Mars. That sounds easy, like it will be a relief. The problem is that your body has just spent months learning that it does not have to support any weight at all. Now it has to remember how to stand, walk, lift, bend, and react when you trip. Inside a bulky, pressurized suit in a place where a fall can rip a seam or crack a visor. The first steps on Mars will not be heroic strides. They will likely be slow, careful movements with backup procedures for almost everything. And here is the bigger issue. We have no real data on what living in 0.38 g for years actually does to a human body. We know what happens at 1 g on Earth. We have decent data for near 0 g in orbit. But Mars sits in the middle, in a zone where we only have guesses and some short experiments. Does 0.38 g stop bone loss? Maybe it slows it down compared to 0 g. Maybe it barely helps. We do not know if your skeleton stabilizes, keeps losing density at a slower rate, or continues to weaken over years. The same goes for muscles and the cardiovascular system. Is 1/3 gravity enough to keep your heart and blood vessels in good shape, or do they still drift toward a base state where they are not strong enough for Earth? If people are ever born and raised on Mars, will their hearts, lungs, and brains develop the same way as children on Earth? Right now, those are open questions. Most of our ideas are based on animal studies in rotating habitats and ground-based analogues, not long-term human trials. So every member of the first crew is not just an explorer, they are a medical data point in a live experiment. Can a human body find a stable, healthy state at 0.38 g? Or does it keep sliding into trouble? On top of the slow changes, you also have to deal with the short-term shock of switching from microgravity to partial gravity. Your inner ear, the system that tells your brain which way is up and how you're moving, has been confused for months. In microgravity, signals from your inner ear do not match what your eyes see. Your brain slowly adapts and builds a new baseline where up and down do not really exist. Then you drop into Martian gravity and everything changes again. Fluids shift back toward your legs. Blood that used to float evenly through your body now has to fight gravity again, even if it is only 0.38 g. Your vestibular system has to recalibrate. The result can be what some astronauts call space fog. Dizziness, nausea, slower reaction times, a general feeling that your brain is lagging behind what your eyes and body are doing. On Mars, that is not a small inconvenience. If you get disoriented and fall while you're in a pressure suit, you risk damaging the suit. A tear or hard impact in the wrong place can mean a leak. A leak on Mars is not like a torn jacket on Earth. Even a small loss of pressure is a direct threat to your life. That is why the first days on the surface will likely be highly scripted. Movements will be conservative. Tasks will be planned with extra time and backup options. The mission will expect that the crew is not at their peak physically or mentally right after landing. They will need time to adapt to 0.38 G before the more demanding work begins. And that work will include something that never goes away: exercise. Microgravity on the way out weakens you. Partial gravity on Mars might not fully fix that. So the only reliable tool you have is training. Just like on the ISS, the Mars habitat will carry treadmills, resistive machines, and other gear designed to load your bones and muscles. You might run in place strapped into a harness. You might use vacuum cylinders or heavy flywheels to simulate lifting weights. But now you face new constraints. Power on Mars is limited and precious. Space inside the habitat is cramped. Time is your scarcest resource. Every hour you spend exercising is an hour you are not using to do science, repair equipment, build new structures, or explore the terrain. The crew has to treat workouts not as optional fitness time, but as core survival tasks, as critical as checking the air filters. Skip a few sessions because you're busy fixing a greenhouse or repairing a rover, and the damage is not immediately obvious. But over months, that neglect adds up. Bone you lose is hard to fully regain, especially at the older ages. Muscle you do not maintain now might be the difference between being able to climb into an ascent vehicle later or needing help. And then there is the final physical hurdle that almost everyone forgets when they picture a Mars mission: coming back to 1G. If you return to Earth after 2 to 3 years of combined microgravity and 0.38 G, you are stepping into an environment that now feels brutally heavy. Some astronauts who came home after just 6 months on the ISS needed help just to stand up, go walk, or go downstairs for a while. They often feel dizzy. Their heart has to work harder again. Their muscles are not ready for full body weight. Now stretch that deconditioning over a multi-year Mars mission. Even if 0.38 G helps a bit, you are still far from normal Earth loading. Landing on Earth could feel like being pinned down. Physical rehab may take months. There may be effects we have not seen yet because nobody has ever done such a long mixed gravity mission. The first Mars crew will answer a question we cannot answer from the ground. Can humans cycle between 0G, 0.38 G, and 1G and still come back truly functional? Or will Mars missions leave permanent changes in balance and strength and health that we just have to accept? And while all of this is going on inside the crew's bodies, there is another moment coming that does not care how strong your legs are or how well your bones have adapted. It only cares about physics, speed, and heat. Because to reach that Martian surface where 0.38 G even matters, you first have to slam into a thin, tricky atmosphere at several kilometers per second and try to land a heavy, human-rated vehicle on a world where we have never landed people before. Landing on Mars is not like landing on Earth with different scenery. It is a whole new class of problem. When your ship reaches Mars, you are moving at several kilometers per second relative to the planet. Robotic missions like Curiosity hit the atmosphere at about 5.9 kilometers per second, around 13,000 miles per hour. A human-rated vehicle carrying a habitat, ascent stage and supplies could be even heavier and faster. The atmosphere you hit is incredibly thin. Surface pressure on Mars is around 600 pascals, roughly 0.6% of Earth's sea level pressure. That's like flying 30 to 35 kilometers above Earth at the edge of space. There is just enough air to compress and heat up in front of your vehicle, turning into super hot plasma that tries to burn through your heat shield. But there is not enough air to slow a tens of ton spacecraft down to something a parachute can safely handle on its own. So you get the worst of both worlds: violent heating without the thick cushion of air that makes landing on Earth easier. Your heat shield has to survive temperatures of thousands of degrees Celsius. The structure behind it has to stay within safe limits so it does not weaken or deform. All the while, your guidance system is trying to control your angle and orientation in an atmosphere that is thin, dusty, and less predictable than Earth's. Come in too steep and you burn or overload the structure. Come in too shallow and you might skip off or overshoot your landing zone. And getting through that first phase is only the start. How do you slow down from hypersonic speed to a safe touchdown when the air is too thin to help you much? On Mars, supersonic parachutes have worked for small payloads. Curiosity and Perseverance both used giant parachutes, deployed at several times the speed of sound, plus a sky crane stage with rocket engines to gently lower a 1-ton rover. That was already pushing the limits of what fabric and lines can handle at those speeds and pressures. Your crewed vehicle is not 1 ton. It could be 20 to 40 tons or even more when you include a habitat and an ascent vehicle. Parachutes alone will not be enough. At those masses, the parachute would have to be unrealistically huge, and even then the thin air would not slow you to a safe landing speed. So the concepts on the table look very different. One option uses hypersonic inflatable decelerators, giant inflatable structures that increase the size of your heat shield so the atmosphere can bleed off more speed. Another option leans hard on retropropulsion, firing powerful rocket engines while you are still moving at supersonic speeds through that thin air. In practice, you probably combine several methods: heat shield, possibly an inflatable drag device, maybe a smaller parachute, and then big rocket burns near the end. Rocket-powered descent in that environment is not simple. The engines have to throttle smoothly while dealing with weird airflow, dust, and rapid changes in altitude. The exhaust plumes hit the ground and kick up dust and rocks that can sandblast your vehicle and sensors. The control system has to keep the ship stable with high precision while everything around it is chaotic. And even if you get the pure aerodynamics and propulsion right, you still have to worry about where you actually touch down. Mars is not a smooth parking lot. High-resolution images from orbit show fields of boulders, sharp rocks, craters, steep slopes, and dust-filled depressions. You do not have the fuel budget to hover for minutes and search around for something that looks nice. You have to pick your landing area before you even arrive. That is why planners define landing ellipses from orbit, zones where the terrain looks relatively safe based on satellite images and maybe previous rover data. During descent, your vehicle will use terrain relative navigation and sensors like LiDAR or radar to compare what it sees with maps stored on board. The system will try to avoid the worst hazards, big rocks, slopes, craters, within that pre-chosen zone, but it cannot work miracles. You might still land kilometers away from your ideal target on ground that is only good enough. Every extra meter off target means longer rover drives, more time outside in suits, and more risk to reach your planned site, cargo, or pre-deployed equipment. Now add one more layer of pressure. There is no way to do a full-scale, full-gravity, full-speed dress rehearsal of this landing on Earth. We can test heat shield materials in wind tunnels and plasma facilities. We can drop models from high-altitude balloons. We can run computer simulations of hypersonic flow and dust interaction. We can test rockets and guidance systems individually, but we cannot simulate 40-ton habitat plus ascent vehicle entering a 0.6% pressure CO2 of our atmosphere, our Mars gravity and Mars temperature, surrounded by real Martian dust anywhere on Earth. The only place that full scenario exists is at Mars. Every robotic landing so far has been a partial practice. They tell us about the atmosphere, the dust, the winds, and how hardware behaves, but your crewed lander will be a different shape, a different mass, a different configuration of engines and tanks. When you go in for that first human landing, your system is flying its first and only real test under actual Martian conditions. If something fundamental is wrong, you find out during the attempt itself. There is no second try. On top of all that is the psychological reality of how alone you really are in those final minutes. During entry, plasma around the vehicle can block radio signals, causing a blackout. Even when you do get telemetry through, Radio signals between Mars and Earth take anywhere from about 4 to more than 20 minutes to travel one way, depending on the distance between the planets at that time. So when Mission Control on Earth hears the call starting entry, the real situation on Mars is already far ahead. By the time that message reaches Earth, you may already have deployed parachutes, fired descent engines, touched down, crashed, or exploded. From your point of view in the cockpit, no one on Earth can help you in real time. They cannot talk you through a problem. They cannot suggest a quick fix. They can only watch delayed data and hope. Inside the cabin, it is just you and your crewmates, strapped into seats or standing at control panels, watching numbers and status lights that represent your actual survival in the next few hundred seconds. Years of training, billions of dollars of hardware, and the entire idea of humans on Mars all compress into that one descent. If the engines light correctly, if the guidance stays stable, if the software does not glitch, if the terrain is as expected, you get to walk away. If any of those ifs fell in the wrong way, there is no rescue. There is only one shot. And the moment those landing legs touch the soil and the dust settles, the next phase of the mission starts immediately. You are now sitting on a planet whose atmosphere is too thin to breathe and too hostile to step into without a pressure suit. You made it through entry and landing, but now you have to stay alive day after day in an environment where just opening the door without gear would kill you in seconds. So the next question is simple and brutal. Once you're on the ground, how do you live on a planet where the air outside your window can quietly destroy your body and your habitat if anything goes wrong? Mars looks calm in pictures, but its atmosphere is one of the most hostile environments humans will ever stand in. At the surface, the pressure is around 600 pascals. That's less than 1% of Earth's sea level pressure, and it's below something called the Armstrong limit. Below that limit, the boiling point of water drops to around normal body temperature. That means if you walked outside without a suit, your saliva and the moisture on your tongue would literally start to boil. You would not explode, but the gas in your lungs would expand, you would not be able to breathe, and you would lose consciousness in a few seconds. Death follows very fast after that. There is no take a deep breath and run. That trick people imagine from vacuum scenes in movies does not apply here. The atmosphere is about 95% carbon dioxide, with only a tiny trace of oxygen. Even if the pressure was higher, there simply is not enough oxygen to keep you alive. Every breath you take on Mars is artificial. It comes from a tank, a recycler, or a machine that has to keep working. So your suit is not clothing. It is a small spacecraft wrapped around your body, holding a pressure of maybe 0.3 to 0.5 bars inside, while the outside is less than 0.01 bar. Any serious puncture, seal failure, or broken valve in that suit does not give you minutes to think. It gives you seconds. The same goes for the habitat. You do not casually open hatches. You do not leave tools lying on seals. You treat pressure retention like your main job, because it is. The air is not the only problem. The temperature swings are brutal. Mars's global average temperature is around minus 63 degrees Celsius, about minus 81 degrees Fahrenheit. That is colder than Antarctica on average. But averages do not tell the full story. Near the equator in summer, in the middle of the day, the temperature at the surface can climb to around 0 to plus 20 degrees Celsius, 32 to 68 degrees Fahrenheit. Sounds almost pleasant. Then night comes. In a single Martian sol, about 24 hours and 39 minutes, the temperature can drop more than 60 degrees Celsius. A comfortable feeling afternoon can turn into deep freeze by early morning. At higher latitudes and near the poles, winter lows can hit minus 125 degrees Celsius, about minus 193 degrees Fahrenheit. At those temperatures, carbon dioxide from the atmosphere can actually freeze out as dry ice on the surface. Every cable, metal beam, plastic fitting, window and battery in your base has to survive those daily cycles of expansion and contraction. Materials expand slightly when heated and shrink when cooled. On Mars, that expansion and contraction is not gentle. It repeats day after day, year after year. Over time, that kind of thermal stress can crack seals, loosen joints, and fatigue metals. Batteries lose performance in cold, so you have to keep them warm. Pipes can freeze, lubricants can thicken or fail. Your habitat is not just holding pressure, it is riding a constant thermal roller coaster. The atmosphere that is trying to kill you by suffocation and pressure loss is also made of a substance you absolutely need: carbon dioxide. CO2 is what you choke on if it builds up in your habitat or suit, but it is also your main raw material for making oxygen on Mars. Technology already tested on the Perseverance rover called MOXIE has shown that you can take Martian air and split CO2 molecules into oxygen and carbon monoxide using solid oxide electrolysis. That was a small experiment producing grams of oxygen per hour. For a crew, you scale that concept up massively. A large CO2 to O2 plant on Mars could refill your air tanks, feed oxygen into the habitat to keep the atmosphere breathable, supply oxidizer for fuel cells that make electricity, and, most critically, produce liquid oxygen for the rocket that will take you off Mars again. Your air becomes a manufactured product with a production target and maintenance schedule. If that system fails, you're not just short on breathable gas. Your entire plan for ascent and power can collapse. So you end up with multiple oxygen sources: CO2 electrolysis, water electrolysis if you have enough water, storage tanks, and chemical backup systems. You monitor the output like your life depends on it, because it does. The same molecule that kills you in high concentration is the feedstock you must force into safe, useful forms every single day. People often picture Mars as calm and still, but it has real weather, and it adds another layer of risk. The air is thin, but winds are real. In major dust storms, wind speeds can reach 60 to 100 kilometers per hour, around 40 to 60 miles per hour. Because the air is so thin, the force you feel on your body is more like a gentle to moderate breeze on Earth. You're not going to get blown over like in a hurricane movie. The real danger is what those winds carry: dust. Martian dust is extremely fine, closer to powder than to sand. When it blows at high speed, it sandblasts surfaces over time. Suit visors can get scratched. External seals, hinges, and joints can wear down. Solar panels slowly lose efficiency as dust sticks and builds up. Radiators that dump waste heat can get coated and insulated, making it harder to cool your systems. Fine dust can infiltrate every small gap. It rides in through airlocks, sticks to suits, settles into filters, and works its way into mechanical parts. Many particles are small enough to get deep into human lungs if they make it inside the habitat. On top of that, Martian dust likely contains reactive chemicals like perchlorates that can interfere with human biology and electronics. That means your air filtration and suit design are fighting a constant war against particles that try to go everywhere you go. And behind all of this is the simple fact that inside your base, you're always living in a pressure experiment. Your habitat interior might be at close to 1 bar of pressure, similar to Earth or at sea level, or maybe a bit lower to save gas and reduce stress on the structure. Outside is less than 0.01 bar. For every square meter of wall, that is roughly 10 tons of force trying to push inward. Every weld in the structure, every bolt hole, every window seal is holding back that pressure 24/7. If a tiny micrometeorite hits the wall and makes a pinhole, that turns into a leak. At first, it might be so small that sensors barely pick it up, a slow drop in internal pressure over hours or days, but if you ignore it, it can grow, or combine with other small leaks, or just drain your limited supply of breathing gas and nitrogen buffer. If a crack forms in a structural joint from thermal cycling, the same thing happens. So leak detection is not an occasional emergency drill, it is a daily routine. You check pressure logs, you listen for hissing with ultrasonic detectors, you use portable sniffers that sense airflow where air should not be moving. If the numbers drift even a little, you start hunting. It is like living in a submarine where the ocean is replaced by a vacuum and poison gas. You can't step outside and wait while someone repairs the hull, you are always inside it. All of these factors, low pressure, toxic air, huge temperature swings, dust, and constant structural stress, create an atmosphere that never truly relaxes. It is always pressing against your technology, trying to find a weakness. And Mars has one more tool it uses to attack that technology and your health. Dust that does not just float in the air but settles into your machines, your lungs, your food system, and even your long-term radiation shield. So the next challenge is simple to state and hard to solve. How do you live and work on a planet where the fine dust under your boots is both your worst contaminant and, at the same time, one of the only materials you have to build real protection? Martian dust is not just dirt. It behaves more like an aggressive chemical powder that wants to follow you everywhere. The grains are extremely small, much finer than typical desert sand on Earth. Think of something closer to talc or subgroup particles than beach sand. On top of that, the dust is often electrostatically charged. When wind moves it around, friction builds static electricity. Charged grains stick to surfaces, cling to fabric, and ride along on anything that passes through. We already saw a version of this with Apollo astronauts on the moon. Lunar dust stuck to suits and visors, scratched seals, and irritated skin and lungs when it got inside the lander. Mars dust adds chemistry to that problem. It likely contains oxidizing compounds like perchlorates, which can react with organic material, your skin, your lungs, your equipment. So every time you cycle an airlock on Mars, dust tries to sneak in on boots, gloves, suit joints and cargo. That means you need aggressive dust control just to keep the inside of the habitat livable. You design airlocks with built-in brushes, vacuum ports, maybe even air showers to knock dust off suits before people come back inside. You add coatings and materials that make dust less likely to stick. But no matter how careful you are, some of it gets through. Over months and years, that slow trickle builds up, and sometimes the planet doesn't just leak dust at you, it throws it in your face. Mars has dust storms that can cover a region, a hemisphere, or the entire planet. Orbiters have watched global storms that last for weeks to months. In 2018, one of these storms dimmed the sun so much that the Opportunity rover, which depended on solar panels, slowly lost power and never woke up again. During a big storm, sunlight at the surface can drop to a small fraction of the normal. The sky turns into a uniform reddish haze. Temperatures on the ground actually become more even. Day is cooler than usual, night is warmer, because the dust blocks and re-radiates heat. Visibility can fall to tens of meters in the worst parts, like being stuck in a dusty twilight all day. If your base relies heavily on solar power, a long dust storm is not just a weather event. It's a crisis. Your solar arrays produce far less power. Batteries start to drain. You may have to shut down non-essential systems, some experiments, some rovers, maybe even certain comfort features in the habitat. You prioritize life support, heating, and communications. If you have a nuclear reactor, you lean on it. If you don't, you're at the mercy of how much energy storage you brought and how long the storm lasts. That's just the energy side. The dust in those storms is also a health risk. On Earth, we know that breathing fine dust can cause serious diseases. Miners get silicosis from inhaling tiny silica particles. People near desert dust events can develop respiratory problems. Martian dust takes that basic problem and adds unknowns. The grains are probably sharp at the microscopic level because there is no liquid water to round them off. They may also carry perchlorates and other reactive chemicals that can interfere with thyroid function and other systems in the body. Inside a well-designed habitat, you filter the air aggressively. You use HEPA-class filters or better. You set up entry zones where dust is removed from clothing before people move into clean areas. But in a closed environment where the same air is recycled for years, even very small leaks of dust into the system could matter. Tiny amounts could slowly accumulate in corners, in ducts, in equipment. The first crews on Mars will not just be explorers. They will effectively be long-term exposure studies. Medical teams will track their lung function, blood chemistry, inflammation markers, and thyroid hormones over time, looking for early signs that Martian dust is doing something harmful, even at low levels. There is no way to fully test this on Earth. You have to live there to find out. While that long-term health question plays out, the mechanical damage starts immediately. Dust works its way into bearings, hinges, and sliding seals. Each grain is like a tiny piece of sandpaper. Over time, it grinds away at moving parts. Rover Spirit and Opportunity both struggled with stuck wheels and wear linked to dust and rough terrain. On a human mission, that same kind of wear can hit rover wheel motors, suit joints at knees and elbows, visor mechanisms, airlock doors, and even the tracks or wheels of construction robots. Radiators and heat exchangers are especially vulnerable. To dump waste heat into space, you expose large surfaces to the thin Martian air. Dust can stick to those surfaces and form a layer that insulates instead of cools. Your thermal control systems have to work harder. Temperatures inside equipment can creep up. Electronics can run hotter and fail sooner. So you respond by over-designing almost everything that touches the outside environment. Bearings get extra seals, joints get protective covers. You add sacrificial layers that are meant to erode so the real structure underneath lasts longer. You schedule regular cleaning EVAs, spacewalks on the surface, to brush off radiators, wipe solar panels, inspect seals, and clear dust from key areas. But every time you send someone outside to clean, you create more chances for dust to ride back in with them. You're stuck in a loop. You must go out to manage dust, and going out brings more dust home. And then there is the twist in this whole story. The same dust and soil that chew up your machines may be the best tool you have to protect yourself from radiation and build real structures. The top layer of Martian soil, called regolith, is a mix of dust, sand, and broken rock. If you pile a few meters of it, say 2 to 3 meters, around 6 to 10 feet, over a habitat, you can dramatically reduce the radiation from cosmic rays and solar storms. The dirt itself acts as a shield, absorbing and scattering particles before they reach the people inside. That means one of the first big jobs for robots and maybe humans on the surface will be moving regolith, pushing it, scooping it, and dumping it on top of pressure vessels like a protective blanket. Regolith also becomes a building material. With the right processing, you can mix it with binders to make concrete-like materials, or heat it with microwaves or focused sunlight to sinter it into solid blocks. 3D printers designed for construction can use this as feedstock to make bricks, arches, landing pads, radiation shelters, and even roads. Instead of shipping tons of building materials from Earth, you turn the local dirt into your main resource. So day to day you fight the dust. Keep it out of your air, away from your lungs, off your equipment. Long term, you rely on the same dust and soil to keep you alive, shielding your habitat from radiation, forming berms around structures, and giving you the raw mass to expand your base. The planet forces you into a strange relationship with its surface. The thing that corrodes your machines is also the thing you must learn to shape and control if you want to stay. But dust and soil are only part of the closed system you're trying to build. You still have to run a complete life support loop. Air, water, food and waste, all circulating in a place where there is no easy resupply and no natural environment to fall back on. So the next challenge is even more unforgiving. How do you build a life support system on Mars where every molecule of air and every drop of water has to be tracked, recovered and reused, and where a small imbalance in that math can end the mission? On Mars, you are not just a person, you're a moving part in a giant math problem. Every day your body takes in and puts out very specific amounts of matter. You breathe in oxygen and breathe out roughly 1 kilogram of carbon dioxide. You drink a few kilograms of water, maybe 2 to 4 litres depending on workload. You eat around 0.7 to 1 kilogram of food. What goes in has to come from somewhere. What comes out cannot just be dumped outside like on Earth. Inside a Martian base, every atom has to be tracked. The life support system has to grab that CO2 before it builds up in the air. It has to pull water out of your sweat, breath and urine, clean it and send it back into your drink bags and plumbing. It has to keep oxygen partial pressure in a narrow, safe range. Too little and you suffocate, too much and you increase fire risk. We already do a version of this on the ISS. There, systems reclaim around 90% of water and scrub CO2 from the cabin air. But the station still gets regular resupply flights. Filters, spare parts and extra tanks of oxygen and nitrogen are delivered from Earth. On Mars, that resupply safety net disappears. You have harsher conditions, longer mission times, and far less margin for error. If you mess up your mass balance there, you cannot fix it by waiting for the next cargo vehicle. That brings us to the most important material in the entire system: water. Mars does not have rivers you can just filter and drink, but we know from orbiters and landers that there is a lot of water locked up as ice, especially under the surface at higher latitudes and maybe in buried deposits near the mid-latitudes. Roughly a cubic metre of ice weighs about a ton. That's 1,000 litres of water, or about 264 gallons. Your job is to turn that frozen resource into a constant clean flow. First, you have to locate usable ice close enough to your base that you can reach it with drills or excavation equipment. Then you have to get to it through layers of dust and rock without clogging drill bits or jamming mechanisms with muddy, dusty ice. Once you dig it out, you melt it, filter out dust and salts, and purify it to drinking quality. After that, that same water does everything. It goes into your drinking supply, it feeds your air recyclers, where it gets split into oxygen and hydrogen if needed. It runs through plant systems in greenhouses or hydroponic setups. It circulates in thermal systems to move heat around. You store it in tanks that double as radiation shielding around sleeping quarters. You can even crack it into hydrogen and oxygen to feed fuel cells, or combined with CO2, make methane and oxygen for rocket fuel. That means losing water on Mars is not just wasteful, it is a direct hit on every part of your life support. Leaks in plumbing, inefficient recovery from air and urine, or poor storage can slowly bleed away your buffer. You have to run the system like a careful accountant, watching where every litre goes, fixing losses fast, and always planning to stay in the black. Air works the same way, just with more chemistry. Mars has plenty of oxygen atoms, but almost none of them are in a form you can breathe. They are locked in CO2 in the atmosphere or bound into minerals in the rocks and dust. So you bring machines that can crack those molecules and free up O2. One proven approach is MOXIE-style solid oxide electrolysis, where you pull in Martian air, compress it, heat it, and split CO2 into carbon monoxide and oxygen using a special ceramic cell. That is one oxygen sun source. Another potential method is to process regolith chemically to release oxygen bound in minerals. Plus you have classic water electrolysis. Split H2O into hydrogen and oxygen if you have enough clean water and power. But here is the key. Oxygen is no longer just air, it is a product with a production rate and a stockpile. You track how many kilograms of O2 you make per day, how many you consume in breathing, leaks, and fuel cells, and how much you need to be building up for your ascent rocket. If one oxygen plant fails, you do not instantly die, but your reserves start ticking down. Maybe you have days or weeks of margin, not months. That is why redundancy drills are baked into the mission. You practice what happens if the main CO2 to O2 unit fails. You switch to backups, reduce consumption, and maybe slow down certain activities. You run simulations of failures while you are still safe, so when something real breaks, the response is automatic. On Mars, air is not a background assumption. It is a schedule, a production line, and a constantly watched number. To push recycling further, you do not just rely on pure hardware. You start using biology, and biology brings its own set of risks. Future missions will likely test bioregenerative systems, algae tanks that soak up CO2 and produce O2, microbial reactors that chew through solid waste and turn it into usable nutrients, maybe even small soil ecosystems that support more complex plants. The idea is to close the loop more tightly, so your life support is not just filters and pumps, but living systems that grow and adapt. But living systems are messy. Microbes mutate. Some strains outcompete others and shift the balance in a tank. Biofilms, slimy layers of bacteria, can form on pipe walls and clog flow. A small change in pH, temperature, or trace chemical levels can push a carefully balanced culture into collapse. You might go from a stable, helpful algae reactor to a smelly, dying tank that produces gas you cannot use and sludge you have to dispose of. So on Mars, you are not only an astronaut and mechanic, you're a farmer of microscopic civilizations. You sample water from bioreactors, check cell counts under a microscope, log pH and nutrient levels, and intervene when things drift. Your plants and microbes effectively become crew members. If they are healthy, your air, water and food are more secure. If they get sick, your whole system is in danger. All of this design work is built on ghosts from past missions. Every time the ISS had a small ammonia leak in its cooling system, it taught engineers how tiny failures show up in telemetry. Every CO2 scrubber issue, like the one on Apollo 13 where the crew had to improvise a fix with tape and canisters, becomes a case study in what can go wrong and how creative humans can be under pressure. Skylab's unexpected condensation and mold issues showed how humidity and temperature control can go sideways in big habitats. Those stories are embedded in every checklist a Mars crew will use. Procedures for changing filters, checking valves, isolating modules, and handling off-nominal readings are all written with past accidents and close calls in mind. The first Mars crew will add their own entries to that playbook, new failure modes we did not predict and new workarounds that save the day. The hope is that all of those stories stay in the category of lessons learned, not causes of loss. So when you put it all together, life support on Mars is not a comfortable background system. It is a tight, closed loop where every human is a moving variable, every machine is a potential single point of failure, and every biological system is both a helper and a risk. You are living inside an equation that has to keep balancing day after day for years. And all of that complexity has to fit inside structures that are sitting under constant pressure, riding huge temperature swings, and taking hits from dust and micrometeorites. Which raises the next problem. How do you actually build and protect a habitat on Mars that can hold this fragile ecosystem together year after year, when the planet itself is constantly pushing and pulling on every bolt and panel? A Mars habitat is not a house on another planet. It is a pressure vessel sitting in a place that constantly tries to tear it open. Structurally, your habitat is basically a spacecraft parked on the ground. It might be a rigid cylinder, a dome, a cluster of metal modules, or even inflatable sections with strong fabric and composite shells. The shape matters. Cylinders and domes spread stress more evenly, so no single panel takes all the load. Inside, you may run close to 1 bar of pressure, similar to Earth at sea level, or maybe a bit lower to save gas and reduce stress on the walls. Outside, Mars sits at around 0.006 bar. That's about a 1 bar difference. For every square metre of wall, that's roughly 10 tons of force trying to crush inward. Imagine a small car pressing on every square metre all the time, every day, for years. So you design walls from strong metals and composites, maybe layered structures with micrometeorite shields on the outside and soft, impact-absorbing layers beneath. If you include inflatable modules, their fabrics are multi-layered. Gas barrier, structural fibers, puncture protection. You analyse how the materials creep over time, how they slowly deform under constant load. And you build in margins so the structure still holds even after years of stress. Then you add the environment, micrometeorites that can hit at tens of kilometers per second, thermal cycles that expand and contract the shell every Martian day, and dust that works its way into seams. Your habitat is never really at rest. It is always fighting vacuum, temperature, and impact at the same time. Radiation adds another slow, invisible force. And the answer to that is to bury yourself. Data from robotic missions shows that Mars's surface radiation dose is around 0.2 millisieverts per day on average, several times higher than on Earth but lower than deep space. If you cover a habitat with 1 to 2 meters of regolith Martian soil and rock, you can cut that down significantly, maybe bringing it close to or even below what you see on the ISS in low Earth orbit. That overburden blocks a lot of cosmic rays and solar particles. That means some of the first machines doing real work on Mars won't be labs or rovers. They'll be dirt movers. Backhoes, bulldozers, or swarms of autonomous digger robots will carve trenches, scoop regolith and dump it on top of habitats. They'll build berms, cover tunnels, and maybe fill protective shells designed to be backfilled with soil. From the outside, a mature base may not look like a sci-fi glass dome. It will look more like a set of low humps and mounds, half-buried modules with only airlocks, antennas and a few unshielded systems visible. You trade pretty views for shielding and survival. Most of the time, your sky is the inside ceiling of a covered tube or dome. Keeping that buried pressure vessel at the right temperature is its own engineering fight, because Mars's thin atmosphere makes normal cooling and heating methods much weaker. On Earth, you rely a lot on convection. Warm air rises, cool air sinks, wind carries heat away from buildings and machines. On Mars, the air is so thin that convection is weak. Most of your heat exchange with the environment happens through radiation. Infrared light leaving surfaces and sunlight hitting them. Your habitat wears radiators like metallic wings or fins, pointed at the sky to dump waste heat into space. Those radiators have to be angled and shielded so they don't absorb too much direct sunlight during the day and don't freeze up too hard at night. Inside the base, pipes move coolant to carry heat from hotspots, electronics racks, life support machinery, greenhouses, out to the radiators. Meanwhile, your interior has to stay in a narrow temperature band. Let it get too cold and water in pipes can freeze and crack fittings. Batteries lose efficiency. Condensation forms where you don't want it. Let it get too hot and you stress electronics, dry out seals and overheat crops in grow modules. The balance is tight. Human bodies, lights, computers, pumps and fans all add heat, and Mars's environment changes daily and seasonally. Thermal control is a constant active process, not a one-time design decision. In the middle of all this cold, another risk shows up that feels almost out of place on an airless desert. Fire. Inside the habitat, you create a comfortable atmosphere for humans. Oxygen, nitrogen, or another buffer gas. Normal pressure, normal humidity. You also pack the interior with plastics, fabrics, foam, wiring, circuit boards, and other flammable materials. That combination is dangerous. We learned that harsh lesson with the Apollo on fire. Oxygen-rich environments and enclosed spaces can turn a small spark into a lethal blaze in seconds. On Mars, if a fire starts in a module, it can fill that space with toxic smoke very quickly. You cannot just open a window or step outside to breathe. Outside is near vacuum and CO2, so you need fast-acting fire suppression systems, gas extinguishers, water mist or foam that can knock down flames without destroying critical electronics. You also design the base with compartments and bulkheads so you can seal off a burning section and keep it from spreading. Crew procedures have to be strict. No unauthorized heaters, no casual smoking, careful handling of solvents, strict upkeep on electrical systems. Fire drills are not optional, because a bad fire does not just damage gear. It can force you to abandon part of your habitat in a place where you have nowhere safe to go. And while all these physical threats are real, there is a quieter one that can eat away at a Mars crew from the inside, the psychology of living in a sealed can with no real outside. On the ISS, astronauts already see that lighting, colours, personal space and noise levels affect a mood and performance. On Mars, those factors are even more important, because you won't have a constant view of Earth's blue curve or quick returns home. Most windows will be small, shielded, or replaced by screens showing camera views, because big transparent areas are weak points in radiation and pressure. That means the interior design of the habitat becomes a mental health tool. Lighting systems may be tuned to simulate Earth's 24-hour day, even though a Martian sol is 24 hours and 39 minutes. You might slowly drift your internal clock or lock it to a schedule that is easy for humans, then adjust work plans around that. Colours and textures can break up the metal box feeling. Warmer tones in living spaces, cooler ones in work areas. Crew need real privacy. Sound-insulated sleeping pods, small personal corners where they can control light, sound, and what they see, even if it's just a screen on the wall. Common areas must be flexible, able to switch from workstations to shared meal space to a place for exercise or movies. All of this is aimed at reducing conflict, depression, and insomnia. So the habitat is not just a pressure shell. It is a machine for survival on 3 levels at once: physical, pressure, temperature, radiation; chemical, air and water; and psychological, sanity, cooperation, motivation. But none of this works without power. Every pump, every fan, every CO2 scrubber, every light in your shirt sleeve world needs energy. On a cold planet with weak sunlight and global dust storm, power is never just a convenience. It's the master resource that keeps everything else running. So the next problem is the one that quietly controls all the others. How do you find and protect enough watts on Mars to keep a whole human outpost alive when the sky can go dark for weeks? On Mars, power is not a utility. It is your life expectancy measured in watts. Start with sunlight. Because Mars orbits farther from the Sun than Earth, it gets only about 43% of the solar intensity we have here. If a panel on Earth reliably gives you 1 kilowatt under good conditions, the same panel onto Mars might average more like 0.4 kilowatts before you even think about dust or winter. In practical terms, everything electric you want to do on Mars, run air pumps, heat habitats, power labs, charge rovers, costs more square meters of solar array than it would on Earth. So you end up designing huge solar farms just to cover the basics. Arrays spread over thousands of square meters, maybe like several football fields worth of panels, just to keep a small outpost running. You add tracking systems so panels tilt and rotate to follow the sun across the sky, clawing back every bit of efficiency. You stretch panels along roofs, over equipment, maybe even over parking structures for rovers, and that's still only half the story because the sun's angle changes with season. In winter, especially at higher latitudes, the sun sits lower on the horizon and days are shorter. That means lower output exactly when you need more power for heating, so you can't just size your solar arrays for the nice days. You size them for the worst case you can afford, then accept that most of the year you're operating closer to the limit than you'd like. Even with all that glass and silicon, solar alone is not enough to keep you safe. That's why almost every serious Mars mission concept includes a second, denser power source, nuclear. A small fission reactor on Mars acts like a heartbeat for the whole base. Designs range from tens of kilowatts to maybe a megawatt or more. Unlike solar panels, a reactor doesn't care if the sky is hazy or if a global dust storm blocks most of the light. As long as its control systems and cooling work, it just keeps producing steady power, day and night, summer and winter. But building and operating a reactor on another planet is not simple. You have to land heavily shielded nuclear fuel safely on Mars, transport it to a safe distance from the main habitat, and set up a system that keeps the core cooled and controlled. You need shielding around the reactor to protect crew and electronics from radiation, but not so much that the whole unit becomes impossibly heavy to land. You have to dump the reactor's waste heat using radiators, just like your habitat but at higher power levels. On Earth, nuclear plants have large teams of specialists, constant inspections and access to spare parts and backup system. On Mars, you might have a crew of 6 to 10 people and a box of spares that took years to ship. Any issue with the reactor, sensor faults, coolant leaks, control glitches, becomes an A-level emergency. You design for fail-safe behavior. If something goes wrong, the reactor should shut itself down in a stable state rather than overshoot. But a shut-down reactor in the middle of a dust storm just hands you a new problem: how to power the base without your most reliable source. That's where energy storage comes in, and where the cost of every watt-hour becomes painfully obvious. A Martian night lasts about 12 hours, roughly like Earth. With only solar power, you need enough storage, batteries, flywheels, or regenerative fuel cells to get through every night when panels are dark. Now add dust storms. In a big one, your panels might generate only a small fraction of their normal output for days or even weeks. That stretches your night into a kind of rolling blackout that can last as long as the storm does. To handle that, you scale your storage systems for more than a single day. You think in terms of multi-day blackouts. That means huge battery banks, stacks of fuel cells with hydrogen and oxygen tanks, or other advanced storage methods. Every extra watt-hour you want to store on Mars has to be launched from Earth as battery mass, tank mass, or extra hardware. And launch mass is brutally expensive. So you hit a hard trade. More storage means more safety, but higher cost and complexity. Less storage means you risk having to turn systems off in a long storm. In a crisis, that might mean dimming lights, cutting back on science operations, limiting rover use, or even lowering the temperature in parts of the habitat to save power, a controlled slide toward the minimum you need to stay alive. Because of all this, power on Mars turns into the invisible currency behind every decision. Every subsystem has a power price tag: water extraction, pumps, heaters, filters, oxygen generation, compressors, electrolysis units, control systems, greenhouses, LED, grow lights, pumps, fans, nutrient circulators, rovers, traction motors, life support in pressurized cabins, sensors, communications, high-gain antennas, amplifiers, computers. When scientists propose a new experiment, it is not enough to ask, do we have room? They have to ask, can we afford the watts? Maybe the new instrument draws 500 watts when running. That might sound small, but if your whole base has a steady 50 kilowatt budget, that's 1% of all available power tied up in one device. If several systems want their share at the same time, something has to give. You get situations where power decisions are almost moral choices. Do you keep greenhouse lights at full brightness to maximize food and oxygen output, or do you dim them to divert power to a long-range rover mission that could discover crucial resources or science targets? Do you run a heavy water mining operation right now, or delay it to leave margin for heating during an oncoming storm? On Earth, power is usually an afterthought, something you assume is there. On Mars, it's the first column in every planning spreadsheet. And hanging over all of this is the constant problem you met earlier: dust. Dust does not just threaten mechanical parts, it directly attacks your power supply. Solar panels on Mars naturally collect dust. It settles out of the air, sticks via static charge, and builds up slowly over time. During storms, it can collect faster. A thin layer cuts efficiency. A thick layer can knock panel output down to a fraction of what it should be. Rovers like Spirit and Opportunity had their lifetimes extended because wind events sometimes cleaned their panels by chance. You cannot plan a human mission around random gusts doing your maintenance for you. So dust mitigation becomes a core technology area. You might use mechanical wipers that sweep across panel surfaces. You might build panels that tilt or flip so dust slides off or can be shaken loose. Electrostatic cleaning systems can charge panels and repel dust grains. Small robot crawlers could patrol arrays, brushing or vacuuming as they go, like solar farm Roombas. Even with these technologies, manual cleaning EVAs will be on the schedule. Go outside and sweep the solar farm becomes a regular task. Crews will walk along rows of panels with brushes and tools, checking for damage and clearing stub and build-up. Every time they do that, they're balancing the gain in power against the risk and time of being in suits, plus the added problem of dragging more dust back toward the base. So power on Mars is a three-way fight. Sunlight that is weak and unreliable, nuclear systems that are powerful but complex and hard to maintain, and dust that wants to choke everything you build. The result is a constant tension where every watt counts and every storm forecast can change your entire week. And yet, having power is only half of staying alive. You still need something to convert that energy into: food in your stomach, microbes in balance, and a growing, stable ecosystem that can live off what Mars can offer. So the next challenge moves from hardware to biology. If you can't ship enough food for years and resupply is rare, how do you grow a living, changing food system on a dead planet without losing control of the microbes that come with it? Shipping all your food from Earth to Mars works on paper until you see the numbers. Take a crew of 6 people on a 2 to 3 year mission. If each person eats around 1 kilogram of food per day, including water content in the food, you're looking at several tons per person over the full mission. Add packaging, safety margins and variety, and you quickly hit tens of tons of cargo. Every extra ton is another launch, another complex transfer, another cost spike. You'll bring a lot of pre-packaged food. It's stable, known so and safe. But if you rely only on that, you get 2 big problems: mass and monotony. Astronauts on the ISS already report menu fatigue on missions that are only months long. Stretch that to years, with no fresh food at all, and you start hurting morale and eventually health. So serious Mars missions will push hard on early plant growth. You start small, racks of leafy greens, microgreens, maybe dwarf tomatoes and peppers in controlled environment agriculture modules. Potatoes and grains might follow a system scale up. The model is similar to experiments on the ISS, LED lights, hydroponic or aeroponic systems, controlled air, but much bigger and more integrated into the base. Now plants stop being just extra snacks, they become part of the life support hardware. Plants take in CO2 and release O2. They transpire water vapour. They fix carbon into biomass. In a sealed greenhouse, you can tune CO2 levels, light intensity, nutrient flow and temperature to get the best yield per square metre. You run LEDs with specific wavelengths that plants use most efficiently, usually red and blue with some white for balance. You keep CO2 higher than normal Earth levels to drive faster growth, as long as it's still safe for humans if they work in that space. Hydroponics, growing plants in flowing nutrient solutions instead of soil, lets you fine-tune exactly what minerals the plants receive. Aeroponics, spraying roots with nutrient mist in air, can use even less water and allow more oxygen around the roots, sometimes boosting growth. Either way, your garden is basically plumbing, pumps, tanks and sensors with leaves on top. And those leaves are more than food. Their performance tells you how the system is doing. If leaves yellow in a certain pattern, you may have a nitrogen problem. If roots brown, maybe oxygen levels in the water are low. Mold on stems might mean humidity is too high. In that sense, the plants are living status indicators for air quality, or water chemistry, and microbiological balance. Your salad doubles as an early warning system, but plants and humans are only half the biological story. The other half is microbes, and you bring an entire invisible ecosystem with you, whether you like it or not. Every person on the crew carries trillions of microbes in their gut, on their skin, in their mouths and noses. The habitat itself will quickly develop its own microbiome, bacteria and fungi on surfaces, in air filters, in water lines, in food systems. Some will come from Earth deliberately, in things like yogurt cultures or soil additives. Others just hitch a ride. In a closed habitat, microbial populations can drift in strange ways. Some species might become more common because the environment favours them. Constant warmth, human skin flakes, small spills of nutrients. Others may die out because they never find a niche. Biofilms, slimy colonies, can build up inside pipes and tanks, clogging filters and changing the chemistry of water. Cleaning routines and disinfectants shape this microscopic world too. If you rely heavily on one kind of biocide, you may push certain microbes to evolve resistance, just like in hospitals on Earth. Over years, you can end up with a microbial community very different from what you launched with, including strains we've never seen before in that exact environment. So part of running a Mars base is essentially game managing an invisible ecosystem. You sample air and water regularly. You swab surfaces and culture what grows. You sequence DNA to track which microbial species are present and how they change over time. You adjust cleaning strategies, change filters, and sometimes fully sterilize parts of the system if something problematic shows up. You are not managing one species, humans. You are managing a small evolving biosphere. Then there is the planet itself. People like to say just plant a potato in Martian soil, thanks to movies, but real Martian regolith is not soil in the way farmers mean it. Soil on Earth is a mix of mineral particles plus organic matter and living microbes. Mars regolith is crushed rock and dust with almost no organic material. On top of that, it likely contains perchlorates and other salts in amounts that are toxic to plants and humans. It also has no natural structure that supports root life. So you cannot directly scoop Mars dirt into a pot and expect healthy crops. You need treatment. One option is washing, flushing regolith with water to dissolve and remove perchlorates and salts, then drying and reusing that water with filtration. Another is chemical treatment to neutralize harmful compounds. A third is to skip soil entirely and only use regolith as a physical medium, with all nutrients supplied by hydroponic solution like an inert gravel. Experiments on Earth using Mars analog materials show that with enough processing and added nutrients, you can grow plants. But doing that at scale, under real Martian gravity and radiation, is a different challenge. And on Mars, failure doesn't just mean bad yields, it can mean serious pressure on your food supplies. Hunger becomes part of the risk calculation. Food ties directly into psychology. On a mission this long, what you eat affects how you think and feel. Astronauts already get tired of certain dishes on the ISS after a few months. On Mars, the stakes are higher. You're stuck with the same small group of people, the same walls, the same routines, and no real way out. Food becomes one of the few things that can change day to day. A handful of fresh herbs, a crunchy leaf of lettuce, the smell of real basil, or a rare piece of fruit from an experimental tree can become a big emotional event. Group meals matter. Sitting down together to eat at the same time, even if the food is simple, creates structure and connection. Celebrating milestones with special dishes, maybe food you've saved, or a first harvest of something new, becomes a way to mark time and keep people grounded. Cooking itself, even in a limited way, gives crew a sense of control and creativity. So the food system is more than logistics and biology. It's culture. It's how the first Mars settlers will define normal life on another planet. What they grow, how they share it, the recipes they invent with limited ingredients. Neglect that and you risk more than grumpy astronauts. You risk depression, conflict, and burnout. All along, the plants and microbes and humans are feeding back into each other. Air, water, waste emissions, forming a fragile ecosystem sealed inside metal and dirt on a dead world. But to explore that world beyond the airlock, to reach the ice deposits, cliffs, lava tubes and rock layers that hold Mars's history, you have to put humans in suits and send them out into an environment where every step is a risk calculation. So the next challenge moves from the inside of the habitat to the open ground outside. How do you work, travel, and do real science in 0.38 G inside a fragile pressure suit, knowing that a single bad fall or stuck rover can turn a normal day into a survival emergency? Outside the habitat, your body is not just a person in a suit. It's a fragile pressure vessel inside a bigger pressure vessel. A Mars EVA suit is basically a mini habitat wrapped around you at something like 0.3 to 0.5 bar internal pressure. That's less than sea level, but still a huge difference from the near vacuum outside. Your skin, lungs and eyes are depending on that thin shell of composite fabric layers and joints to keep your blood from boiling and your lungs from collapsing. Current suit designs, like the ones used in orbit and tested for the moon, are stiff. Every time you bend an elbow or knee, every time you twist your torso, you're fighting the pressure inside the suit. The gas wants to keep the joints round and expanded. You want to flex them. That takes real effort. Mars suits may improve this with better bearings, lighter materials, or even mechanical counterpressure designs that use tight, flexible layers instead of just gas pressure. But no matter how advanced they are, you will burn a lot of calories just moving. A typical EVA might last 6 to 8 hours. For that entire time, your life depends on pumps, valves, filters, and seals that you cannot directly see. Your backpack, the portable life support system, controls suit pressure, scrubs CO2, delivers oxygen, regulates temperature, and handles cooling water that pulls heat away from your body. A blockage or leak in any of those lines is not just an inconvenience. It can overheat you, suffocate you, or drop your pressure dangerously fast. You watch your suit telemetry constantly. Tank levels, pressures, flow rates, battery charge. You listen for subtle changes in pump noises. Trust in the suit is not automatic. It's earned every minute it keeps you alive. Now, add Martian gravity to that situation. At 0.38 G, you're lighter than on Earth. But your mass, your inertia, does not change. That means it's easier to lift your own body, but once you start moving, it's still just as hard to stop or change direction. inside a bulky, slightly stiff suit that becomes a trap. If you push off a rock or a rover too hard, your lighter weight makes you accelerate faster than your instincts expect. You might lurch forward, start to tip, and find that your ability to correct is limited by suit stiffness and limited grip. Apollo footage on the Moon, at 1/6 G, shows astronauts stumbling and falling just from small misjudgments. On Mars, with higher gravity than the Moon, but still well below Earth, the motions will feel different again. The first crew will have to invent a safe Mars walk. Maybe it's a kind of careful shuffle with low steps to keep your centre of mass stable. Maybe you lean more forward and keep your feet closer to the ground to avoid long floating strides. They'll run drills near the habitat in controlled conditions to figure out how to climb slopes, descend into small craters, and handle tools without overbalancing. Falling is not just embarrassing. A bad fall can crack a visor, damage a suit joint, or knock connectors loose. On Mars, that can be lethal. To go beyond walking distance, you won't just hike. You'll extend your body with machines, pressurized rovers. A pressurized rover is like a small mobile habitat on wheels. It has its own air, its own life support, and its own power. You can get out of your suits inside it, work at shirt sleeve pressure, sleep, and travel tens of kilometers from the base. That massively increases your range for science and resource hunting. You can reach ice deposits, complex rock formations, and distant lava tubes that would be impossible on foot. But the rover adds new failure modes. Wheels can get stuck in soft soil, like Spirit's wheel did on Mars. Motors can burn out. Suspension components can fail under repeated stress. The rover's own life support can have leaks or CO2 removal issues. Software can glitch, locking up controls or mismanaging power. If you're 20 or 30 kilometers from the base, 12 to 18 miles, and the rover dies, you cannot just walk home in suits unless that's been planned for and the timing, terrain, and suit consumables all line up perfectly. Your survival comes down to redundancy, spare parts you brought, tools you have, your ability to repair on the spot, and how much air, water, and a battery the rover carries in reserve. The rover is your second skin. When it gets sick, you're immediately at risk. While you're out there, you're also the only human eyes and brains on the ground. On Apollo, astronauts talk to mission control with only a short delay. Geologists in Houston could suggest which rocks to sample, which outcrops to climb, almost in real time. On Mars, radio delay between you and Earth is 4 to more than 20 minutes one way. That's up to 40 plus minutes for a question and answer loop. Fieldwork can't wait that long for every decision. You will get pre-planned traverses and waypoints based on orbital images, like drive to this crater rim, or sample this layered outcrop. You'll have high-resolution maps and maybe even drone surveys to guide you. But when you're standing there looking at a rock that looks strange or a fracture that wasn't visible from orbit, you have to make the call. Which sample jars do you use? Do you risk a short climb? Do you spend another 20 minutes drilling here or move on? You're not just hands for Earth-based scientists. You're their on-site representative, making judgment calls that can't be reversed. If you skip something important, it might be decades before anyone gets back to that exact spot. If you push too hard and damage equipment or suits, you can't just shrug it off. Every decision is science mixed with risk management, which leads to the final reality. Every EVA is a calculated gamble. Suits age, seals wear, zippers, bearings, and visors degrade in the dust. The more time you spend outside, the more you use up that limited lifetime. You monitor how many hours each suit has logged, how many pressure cycles each airlock has seen, how many times each helmet has been cleaned. Planning an EVA becomes an optimization problem. Do you send 2 people or 3? 2 means fewer consumables and less suit wear, but less redundancy if something goes wrong. 3 gives you more hands and backup, but uses more air, water, and power, and exposes a bigger fraction of the crew to risk. Do you push 1 more kilometer to reach a promising rock outcrop, knowing that it will burn extra battery and air, and that turning back later might be tight on margins? Or do you stop short, preserving consumables and hardware, but giving up data you might never get again? Even small choices matter. How many tools do you carry versus how much mobility do you keep? Do you schedule a second EVA tomorrow to finish a task, adding more risk days, or do you push harder today while you're already out, increasing fatigue? The planet itself is the unknown variable. Slopes that are steeper than they look, dust that's softer than expected, rocks that break tools. Outside on Mars, you're never just taking a walk. You're managing the life of a human in a fragile shell, the health of machines that keep that human alive, and the goals of a mission that only gets one first chance at this world. And as you work further and further from the habitat, another kind of distance starts to grow, the distance between your mind and the people back on Earth. Conversations stretch out to nearly an hour round trip. Your only real social world is the small crew around you, so the next challenge steps inside your head. What does it actually do to people when every call home is delayed? Your whole in-person universe fits in a single room, and even the length of a day is just slightly wrong for the human body. On Mars, even a simple conversation with Earth happens in slow motion. The distance between the planets changes as they move around the Sun, and with it the radio delay. At best, signals take about 4 minutes one way, at worst more than 20 minutes. That's up to 40 plus minutes for a question and answer. You cannot say we have a leak, what do we do, and wait for mission control to talk you through each step. By the time a reply arrives, the situation will have already evolved. So real-time problem-solving shifts almost completely to the crew. Earth turns into a slow, thoughtful advisor. You send detailed descriptions, data logs and video. They send back analysis, suggestions and long-term planning. But in the moment, when a pump fails, a rover gets stuck, or a crewmate shows worrying symptoms, decisions are local. The commander and the team on Mars own the outcome in a way ISS crews never fully do. That delay also changes how you experience home. Messages from family come in batches. You reply, then wait. There is no quick call me back, no live video chat where you can instantly see someone's reaction. Emotional support becomes asynchronous. You learn to write and speak to people who won't answer for almost an hour. Earth becomes a distant, slow echo, not a real-time presence. Inside the habitat, your social world shrinks even more. Your in-person universe is 4 to 8 people total for years. No new faces, no going for a walk alone in a city, no slipping away to another group of friends. The closest analogues on Earth are Antarctic winter crews and submarines, and even they know that in a real emergency, evacuation is at least possible. On Mars, it's not. Small annoyances can't be escaped. The person who chews too loudly, the one who leaves tools in the wrong place, the one whose jokes landed back on day 10 but great on day 300. Those are the same people you depend on for your life in a fire, a leak or a medical crisis. You cannot just avoid them, you have to fix the relationship. That's why crew selection and training become as crucial as any engineering system. You don't just pick people who are technically excellent, you pick people who can handle conflict, who are honest about stress, who can apologize and forgive. You train in group psychology, communication under pressure, and structured debriefs. You practice resolving real disagreements, not just fake scenarios, before anyone even leaves Earth. A weak dynamic on Mars is not just uncomfortable, it's dangerous. Then there's the planet's own rhythm, which doesn't quite match what your body expects. A Martian day, a sol, is about 24 hours and 39 minutes. That extra 39 minutes sounds small, but it matters. Your internal clock is tuned for roughly 24 hours. On Earth, you can push it a bit with light cues, caffeine and routines. On Mars, if you try to fully sync with Earth time and mission schedules, that mismatch accumulates. We've already seen how hard this is from Mars rover teams on Earth. When they lived on Mars time to match rover operations, their workday slid by 39 minutes every day. After a few weeks, they were effectively working in the middle of the night local time and reported serious sleep problems and fatigue. On Mars itself, you'll probably lock into local sol time. You get up with the same sunrise, eat and work by the same habitat clock, sleep at the same local night. That's simpler for the body. But it means every schedule with Earth, teleconferences, data downlinks, planned updates, has to be translated between two clocks that drift against each other. Your day length is now slightly alien, and you live with that every single soul. When you do get a moment to look outside, the sky gives you another reminder of just how far you've gone. From Mars, Earth is not a huge disk hanging over the horizon like the Moon is for us. To the naked eye, it looks like a very bright star. With a small telescope or zoom camera, you might make out a tiny disk, maybe even hints of phases as Earth orbits the sun, but you're not seeing continents, weather patterns, or familiar geography with your own eyes. The famous Earthrise moment from Apollo, seeing your entire home world rising above a barren horizon, that simply doesn't exist in the same way from Mars. Your home is a point of light in a different part of the sky, sometimes visible, sometimes lost in daylight or dust. Intellectually, you know billions of people live on that dot. Emotionally, it can start to feel like somewhere else entirely. Your sense of distance rewires. Home is no longer down there, it's up there, far away, unreachable for years. Put together, long communication delays, tiny social circles, an off-kilter day length, and a sky where Earth is just another bright point. That's a heavy psychological load before you even factor in the constant background stress. Because in the back of your mind, you're always aware of the hard edges, radiation exposure accumulating over time, the possibility of a sudden habitat leak, the fact that there is no emergency return. Polar station crews on Earth already show higher rates of depression, sleep disorders, and irritability. On Mars, you stack those issues with, if something big fails, we die here. That's why mental health has to be treated as core systems engineering, not a soft extra. The mission design has to bake in structured downtime, not just empty hours. That means fixed off-duty blocks where no one is allowed to schedule maintenance or experiments. It means planned group activities, not just hang out if you feel like it. Telepsychology sessions with professionals on Earth become routine, even if they're delayed and happen over recorded messages. Virtual reality systems might simulate forests, oceans, or home cities to give your brain something other than metal walls and dust to process. Creative projects, music, writing, art, building, things from 3D printed junk parts get treated not as hobbies, but as maintenance for the mind. Rituals matter too. Weekly debriefs where everyone can speak freely. Regular crew meetings that are not just about tasks, but about how people are coping. Celebrations of milestones. First year on Mars, first harvest of a new crop, completion of a big construction project. All of that keeps the mission from turning into an endless grey blur. Because if you ignore mental health on Mars, everything else, life support, power, suits, rovers, starts to fail in slower, more human ways. Bad decisions, missed warnings, conflicts that distract from critical maintenance. A burned-out, resentful crew is as dangerous as a faulty pump. And through all of this, you're living on a world that might hold something we've been chasing for decades, signs of life that didn't start on Earth. So the next challenge adds a new kind of pressure on top of survival. How do you search for alien life in Mars's rocks and ice without accidentally wiping it out with your own microbes or bringing something unknown back with you? On Mars, survival is your first job, but right behind it is a question humans have asked for centuries. Are we alone? Mars is one of the best places we know to look for an answer. The planet has ancient river valleys, dried up lake beds, and delta deposits where water once pooled and flowed. Rovers have found clays that form in water and organic molecules locked into sedimentary rocks that are billions of years old. Those rocks are exactly the kind of places on Earth where we find microfossils, tiny remains of bacteria and other simple life. If life ever started on Mars, it was almost certainly microbial. Maybe it thrived when the planet was warmer and wetter, then retreated underground as the surface dried and the atmosphere thinned. Today it might survive in briny pockets under the ground near buried ice, or in zones heated a little by the planet's interior. Or maybe it died out completely and left only chemical fingerprints behind. As a member of the first crew, you may walk up to rocks that preserve that story in layers only a few centimeters thick. You might drill into sediments that have been sealed for billions of years. You might pull up samples of ice or salty dirt from just below the surface that could still, in theory, host simple life. But here's the catch. You're covered in life from Earth. Planetary protection rules already limit how we send spacecraft to Mars. We sterilize hardware, track microbial loads, and avoid certain regions with high potential for liquid water because we don't want to dump Earth bacteria into an environment that could support native life. If we do, it becomes much harder, maybe impossible, to tell what's Martian and what's contamination. Now replace a small baked-out robot with a human. You are a walking cloud of bacteria and viruses. Even in a clean suit, your skin, breath, and waste can spread microbes. On Earth, that's normal. On Mars, it's a threat to the very science mission you came to do, so your movements will be tightly controlled in some areas. Regions with subsurface ice, recurring slope lineae, those dark streaks that might be related to salty flows, or certain kinds of clays and salts will likely fall under stricter rules. You may need special decontamination steps before and after visiting them. Tools and drills may be sterilized between sites. You might be banned from physically entering some zones at all, relying on sterilized robots to do the close-in work while you stay back. That can feel like handcuffs, especially when you see an interesting feature just beyond a boundary line on your map. But the risk is real. If you seed a potentially habitable niche with hardy Earth microbes, you could wipe out or overwhelm any fragile native biology, or make it impossible to prove it ever existed. Even if you protect Mars from us, the science of life detection is less straightforward than people think. Back in the 1970s, the Viking landers ran the first dedicated life detection experiments on Mars. One test seemed to detect metabolism when Martian soil was given nutrients. Other tests and chemistry results didn't match that signal. Decades later, scientists still argue about what those data meant. Were they seeing life, or just unusual surface chemistry and very reactive soil? Modern instruments are smarter. They look for specific organic molecules, patterns of carbon isotopes that hint at biological processing, and complex structures or combinations that are unlikely to appear by chance. On a crewed mission, you might have compact labs able to sequence DNA or RNA, scan for a wide range of organic compounds, and measure extremely fine chemical details right there on Mars. But a positive result is not a simple yes or no. Let's say you detect something that looks like a cell, or a molecule pattern that screams biology on Earth. You still have to prove it didn't come from your own contamination. You'd run controls, compare with known Earth microbes, test for weird biochemistry, different handedness of molecules, different bases than Earth DNA, unusual cell structures. Even then, a single ambiguous result could ignite years of debate back home. You might leave Mars with more questions than answers, signals that look like life but don't quite fit, or environments that seem perfect for microbes but test sterile. Life detection on Mars is not just about success. It's about being honest about uncertainty. While you're worrying about contaminating Mars, planners on Earth are worrying about the opposite. Mars contaminating Earth. Bringing Mars samples home safely is one of the hardest parts of this whole story. Rocks or ice that you collect will likely be sealed in multiple layers of containers, each designed to survive launch from Mars, the trip through space, re-entry to Earth and landing. When they arrive, they won't go to a normal lab. They'll go to a high biocontainment facility, similar in some ways to labs that handle dangerous viruses, but tuned for things we don't fully understand. The fear isn't movie monster aliens. It's more subtle. What if a Martian microbe or some weird chemical system can survive in Earth conditions and interact with our biosphere in ways we can't fully predict? That could be harmless, it could be useful, or it could be bad. Until we know, we treat every Mars sample as potentially sensitive. For you as a crew member, that means anything you bring back, rocks, ice cores, even used filters and wipes, could become some of the most heavily guarded scientific material in history. Handling protocols, transport containers, and chain of custody rules will be extreme. If humans themselves eventually return to Earth after long exposure to Martian dust and possible microbes, Medical quarantine and testing may look more like planetary protection than standard health checks. You're not just returning astronauts, you're returning part of Mars. Underneath all of this technical work sits a deeper consequence. If you find clear evidence of life that did not originate on Earth, even if it's just simple microbes, that means the universe didn't produce life only once, it did it at least twice on 2 neighbouring worlds around the same star. That would suggest that given the right conditions, life might be a common outcome, not a rare fluke. That single result would ripple through biology, forcing us to redraw the tree of life with a second trunk. It would hit philosophy, challenging long-held ideas about humanity's uniqueness. It would change how we look at every exoplanet we've found, turning many of them from maybe interesting rocks into possible ecosystems. Even the opposite result, a thorough, careful search that finds no life past or present anywhere on Mars, would be just as powerful. If a planet had water, energy, and billions of years never managed to produce life, that says something about how special Earth might be, and how fragile those conditions are. It would push us to ask why this world succeeded when a near twin did not. Either way, your mission doesn't just add a chapter to science textbooks, it rewrites the introduction. And while you're chasing those answers in rocks and ice, another question is tightening around you. If humans are really going to stay on Mars, build bases, mine ice, and maybe raise families, who decides the rules? So the next challenge shifts from geology and biology to ethics. When you stand on Mars in a suit with a flag on your shoulder, a corporate logo on your rover, and international treaties in your mission plan, who actually runs this new world? And what are you allowed to do there? On paper, Mars already has rules. In practice, those rules have never been tested by people who actually live there. The key document is the Outer Space Treaty. It says no nation can claim sovereignty over the Moon, Mars, or any other celestial body. You can't plant a flag and declare, "This is now the territory of country X." Space is supposed to belong to all humanity, but reality on the ground looks different. Someone will own the rockets that brought you there. Someone will own the habitat, the reactors, the rovers, and the software that controls them. That someone might be a government space agency, a private company, or a mix of partners. Whoever holds that power effectively controls your life. If they decide how much oxygen you get, what missions you run, and when you can launch home, they have more influence over you than any flag. As crew, you live in a grey zone. You're subject to the laws of your home country, to international agreements, and to mission-specific codes of conduct drafted by lawyers who have never set foot on Mars. If your team includes astronauts from multiple nations, or government and private astronauts together, the legal picture gets even murkier. Which laws apply in a dispute? Who investigates if someone commits a crime, or even something as simple as theft or assault? Right now, the written framework is thin. You become the test case that shows where it holds and where it breaks. At the same time, practical authority shifts heavily from Earth to the commander on Mars. On the ISS, ground control in Houston, Moscow, or other centres can watch almost everything in real time. They can step in, override plans, and even order a crew to take specific actions. On Mars, with minutes to tens of minutes of delay each way, that level of control is impossible. If there's a fire in a habitat module, an air leak, or a medical emergency, you and your crewmates handle it yourselves. You can send a brief status update. We've had a leak sealing module now, but by the time Earth reads it, you've already acted. There is no one to talk you through a checklist, step by step. The mission commander's practical power becomes enormous. They decide who goes outside, how risks are allocated, when to abort an operation, and how to respond when someone breaks protocol. Discipline issues are local too. If a crew member refuses to follow rules, puts others at risk, or suffers a psychological breakdown, you can't send them home. You have to manage it where you are, restrict duties, isolate for safety, maybe sedate in extreme medical cases. Earth can review and judge later, but in the moment, your small group is the highest court on the planet. While you're dealing with that, you're also quietly setting the tone for how Mars will be used or exploited. Resources on Mars are not all equal. Some patches of ground will matter far more than others. Water ice close to the surface is gold. It's drinking water, breathable oxygen and rocket fuel feedstock. Metal-rich regolith can feed 3D printers and construction. Deep, stable lava tubes can become natural shelters, requiring less construction and offering built-in radiation protection. Even as the first crew, what you do with those places sets precedent. If you map an ice deposit, do you publish its exact coordinates openly, or do you keep some details restricted for security or future commercial use? If you start mining a patch of ground for your own base, are you just using it, or are you effectively reserving it for your sponsoring nation or company? Are you there purely as scientific stewards, with a duty to minimize disturbance? Or are you the first wave of a long-term settlement and resource operation? The line between research outpost and colonial beachhead can blur quickly, especially once investors and governments see useful materials coming out of the ground. Your field reports and resource logs may later be used by lawyers arguing over who gets to do what on Mars. Then there are the experiments that only Mars makes possible, and that many people on Earth will find deeply uncomfortable. Low gravity and radiation levels on Mars open up controversial research topics. Medical decisions get sharper too. If someone suffers a major injury, spinal damage, severe burns, internal bleeding, you cannot evacuate them to a hospital on Earth. Supplies and trained staff are limited. Experimental surgeries, unproven treatments that would never pass ethics boards on Earth might be the only options. If the alternative is almost certain death, what counts as informed consent? How do you make those calls under pressure, knowing there will be scrutiny years later? Long-term radiation exposure studies also cross ethical lines. On Mars, you are collecting lifetime health data on people deliberately exposed to levels of radiation above Earth norms. You're doing it because there's no way around it. But you're also turning astronauts into subjects in an experiment about the limits of human tolerance. Everyone may have signed forms on Earth, but consent feels different when your hair starts thinning early, your blood markers shift, or you develop symptoms we didn't predict. As all of that plays out, something more subtle is forming around you. A new culture. In a crew of 6 with different nationalities and backgrounds, the culture of Mars starts as tiny things. A shared joke about a glitchy airlock, a Friday night movie ritual, a habit of writing everyone's name on the whiteboard when they go outside. You might give informal names to hills seen in from the habitat windows, or to rovers and robots. But every log entry you write, every internal policy you draft, every way you handle a conflict becomes reference material for future missions. Training programs will quote your procedures. Lawyers will cite your incident reports. New crews will copy the good habits you developed and avoid the bad ones. Without meaning to, you're writing the first chapters of Mars's unwritten constitution. How people speak to each other in emergencies, what counts as fair workload, how leadership rotates or doesn't, how much autonomy local crews have against orders from Earth. Tiny decisions, like how openly you share data with other nations or companies, can snowball into norms that either encourage cooperation or lock in competition. So by the time your mission ends, you haven't just survived under someone else's rules. You've helped create the framework others will live under. Scientists, settlers, maybe entire communities that will never see Earth. And then, after years of living this new legal and ethical reality on another world, you face one last, unforgiving test. Getting off Mars and coming home, knowing that if you succeed, you may also be proving that humans are not just visitors here. We're staying. So the final challenge pulls everything together. How do you launch back into space from a dusty, remote planet in a ship that has never flown before, survive another deep space crossing, and live with what it means if Mars doesn't stay empty after you leave? Leaving Mars is in some ways harder than getting there, because this time you already know exactly how much can go wrong. To go home, you needed an ascent vehicle that has been sitting on Mars for months, maybe years. It has lived through dust storms, temperature swings of tens of degrees, and constant low gravity tugging on its structure. Its tanks may have been slowly filled with fuel made on Mars itself, methane and oxygen produced from local CO2 and imported hydrogen, or from water ice cracked into hydrogen and oxygen. When launch day comes, you climb into a machine that no one has ever flown in exactly these conditions. This exact stack of tanks, lines, valves, pumps and engines has never left Mars before. Testing on Earth and simulations get you close, but they are not the same as real Martian dust, cold-soaked hardware and months of aging. You strap in, check valves, verify tank pressures, run through engine start sequences, and then commit. You light engines that have to push you to around 4 kilometers per second of orbital speed, about 9,000 miles per hour, through a thin atmosphere with almost no help from aerodynamics. There is no abort tower, no cut engines and land back on the pad option that is actually safe. If an engine fails badly at the wrong moment, there is nowhere to go but down. For those minutes of ascent, everything — navigation computers, guidance thrusters, main engines, fuel mixture ratios — has to work well enough on the first try. If it does, you separate from lower stages, align in a parking orbit around Mars, and finally see the planet from above instead of below. If it doesn't, there's no rescue capsule in orbit, no second ascent vehicle waiting. Even after you reach orbit, you're only halfway through the departure. You still have to rendezvous and dock with your return vehicle or Earth transfer stage. Maybe that return ship has been waiting in Mars orbit since before you landed. Maybe it arrived later with extra cargo. In either case, just like at the ISS, you need to match orbits, close in to within meters, and make a clean solid docking. The difference this time is delay. When you practice docking near Earth, someone in mission control could watch your telemetry in real time, compare it with simulations, and step in if something looked wrong. Around Mars, that's gone. Even at the best alignment, your radio delay to Earth is still on the order of 10 minutes or more round trip by the time this mission flies. Your computers will handle most of the approach, running automated rendezvous and docking software that has been tested to death. But if something behaves oddly, a sensor glitch, a misread in radar range, a thruster that underperforms, you can't ask Earth, should we back off and try again, and get help in time. In a pinch, it's your hands on the manual controls, your judgment about backing away or pressing forward. Folks on Earth see what you did long after you've already done it. Once you've docked, transferred crew and critical samples, and stowed everything for the trip, you fire the big engines one more time. Mars's gravity well falls behind, the red disk shrinks, and you are back in the deep space corridor between planets, this time heading home. Months later, Earth fills the window again, and you face the last major physical shock — re-entry. Coming back from Mars, you hit Earth's atmosphere at around 11 kilometers per second, about 25,000 miles per hour. That's faster than a typical return from low Earth orbit. Aerothermal loads, frictional heating that turns air into plasma, pound your heat shield. Temperatures on the shield can reach thousands of degrees Celsius. G-forces during peak deceleration might spike to several G, pushing your already weakened body hard into the seat. The capsule structure, tiles, seals and parachutes all have to survive exactly as planned. Dust from Mars may still be trapped in small crevices, but the real danger now is simple physics: too steep and you burn, too shallow and you skip. The guidance software has one chance to thread the path that gets you to a survivable descent. Assuming it works, you deploy parachutes, fire final thrusters if the design uses them, and slam into the ocean or ground. Rescue teams reach you. You're hauled out, suit removed, vitals checked, and flown to medical care. Physically, you're back on Earth, but your body and mind are not what they were when you left. After years of microgravity and 0.38 G, 1 G feels brutal. Your heart has to work harder again. Blood wants to pool in your legs instead of staying comfortably distributed. Standing up can make you dizzy. Muscles that were good enough for Mars feel weak here. Bones that lost density may ache under full weight. You move more carefully than you ever did before spaceflight. Radiation has left its mark too. You might have subtle DNA damage that will only show up in long-term medical data. Blood tests and scans become routine. Doctors will watch for early signs of problems: cataracts, blood changes, increased cancer risks. Psychologically, Earth can feel overwhelming. Bright colours, crowds, weather, noise, open spaces with no pressure walls. Everyday life may feel too easy and too chaotic at the same time. But while you're recovering, researchers are harvesting the most valuable cargo you brought back: data. Every sensor reading from your suit and habitat, every crack and scratch in wall panels, every dust sample analysed, every log entry and psychological survey. All of it feeds into the design of the next missions. Maybe some fears will turn out to be manageable. Radiation a bit lower than expected in well-shielded habitats. Dust storms less damaging to certain systems, crews coping better with isolation than worst-case models predicted. Other problems might be worse. Maybe partial gravity doesn't protect bones and muscles as much as hoped. Maybe long-term exposure to low-level Martian dust inside habitats shows clear health impacts. Maybe some types of equipment fail more often in real Martian conditions than in tests. Those findings will reshape mission architectures. Thicker walls here, new filters there, different EVA schedules, stricter limits on how long people can stay before rotating home, or no rotation at all for some future settlers. Your entire mission becomes the boundary condition in the equation. The first real data point for what a full go there, live there, come back cycle does to humans and hardware. Planners will use your experience to decide whether to scale up to larger outposts, pause and rethink, or change tactics entirely. And then comes the realization that may be harder to process than any G-force. You were never meant to be the last. If your crew makes it back alive and the mission hits even modest goals, safe operations, some good science, a few working demonstrations of in situ resource use, you've just unlocked the public will for more. Follow-up missions will be drawn up. Cargo ships with heavier equipment will be scheduled. Bigger habitats, more robust power systems, and more ambitious science plans will move from concept art to actual contracts. A second base site might be chosen, maybe near a different ice deposit or geologically rich region. Debates will start about permanent infrastructure, long-life reactors, large greenhouses, buried tunnels, maybe even early steps toward a small semi-permanent settlement. At some point, either during your mission or soon after, people on Earth will quietly cross a mental line. Mars will stop being a place we visit and become a place where humans simply are. Not in huge numbers, not yet, but continuously. Someone will always be on their way there, living there, or on their way back. For the first time in 4.5 billion years, Mars will no longer be a completely dead rock on the surface. Life will have a foothold. Your life, your crew's microbes, your greenhouses, your waste systems, your structures filled with air and water. You will have been part of the species that carried an entire biosphere across space and lit it up on another world. That's the weight the first Mars crew carries. Not just surviving the trip, not just planting a flag or taking a selfie, but making decisions and proving systems that decide whether humans remain a one-planet story or become something else entirely. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect, like the video, and subscribe to the channel for more such amazing videos.